nonlinear system, our scope for this topic is similar to the linear system, where students should be able to understand the problem in relation with the system of ODE. Second, you should be able to solve the problem by solving the nonlinear system of equation. And our scope is using the eigenvalue method. And the third things, you should be able to interpret the solutions that you get. We have the besides having the analytical solution using the eigenvalue method, our scope is also about the equilibrium points, about the stability of stability of the equilibrium point, and also analysis part based on the phase portrait. Okay, so here is the one example for the nonlinear system. The problem is the predator-prey problem. Okay, in which here we have, let's say we have two species in one place. Okay, one is the predator and another one is the prey. Okay, so here is the assumptions for this problem. First, in the absence of the predators, we assume that the prey population will grow at a natural rate. Okay, so here recall the problem in the first order model that we see. Population grows at a natural rate. We have this kind of equation, right? So here if we set the variable for the predators population, okay, so based on this assumption, actually we set x as the population for the predator. Sorry, here is the prey population. Okay, so as usual, t is time. This equation means that the prey population grows at a natural rate. Okay, changes of x versus t is equal to growth, so that's why we have positive sign here. A is a constant. Okay, this is the equation. The second assumption is in the absence of the prey, predator population will decline at a natural rate. Okay, so here we set y as the predators population. Okay, so here decline, so that's why in this expression we have negative sign. B is a constant. We have y represent the predators population. So why do we have this assumption? This actually related with the problem. Okay, in this problem we have the predators and prey, where predators depends on prey as their food. Okay, so in this case, when we have absence of predators, so prey able to grow. Okay, because the rate of death, okay, might be small. Okay, so that's why we have positive sign here. While for the second assumption, if we have the absence of prey, so predator having problem in finding foods. Okay, its food sources will be low. Okay, so that's why it leads to the decline of its population. So let's say we assume natural rate for the growth and also for the decline for prey and predator. So we will have this term in the equation. Okay, as usual, before this we learned about the linear system. So uh, uh, considering the two things, in this case the population, in one problem, so that's why we have a system of equation. In this case, two things, so we have two equations. The third assumption here, when both predators and prey present, okay, so here both exist, the prey population will decline. Okay, this is because predators exist, so prey will becomes its food source. So due to this, population for prey will decline, while the predator population will grow. Okay, because it has food sources. Okay, no problem with the food sources, so they manage to grow. Okay, in this case, an assumption for this is at a rate proportional to the frequency of encounters between individuals of the two species. So here is the assumption in this problem is frequency of encounters here is how many times the predators and prey meet, okay, meet with each other. So means that if predators meet prey, then predator will have will make prey as their food. Okay, that's the meaning here, frequency of encounters. Rate proportional to the frequency of encounters. So the third assumption here is actually this term, okay, for the first equation, and this term for the second equation. Okay, so based on these three assumptions, the model for the predator prey is given by this. Okay, we have two equations. The first equation here, x is the prey population. So this is the changes of prey population versus time. The second equation, dy dt, is the predators population changes versus time. The right hand side here, for the first equation, the first term comes from the first assumption. Okay, in the absence of the predators, the prey managed to grow naturally, so we have a x term. And then the last term in the first equation is from the last assumption here. We have negative pxy. Okay, pxy here comes from this assumption, rate proportional to the frequency of encounters here means x meeting y, so x multiply with y. Okay, when predator x here prey meeting the predator. Okay, that is how we can understand this term, x multiply with y. Rate proportional, so as what we learned in the first order case, rate proportional, there will be this term multiplied with the constant. Okay, or in this case we use constant p. P is constant, pq is a other constants. Okay, so why do we have negative sign here? Because the first equation is for the prey population. So when prey meet the predator, possible okay, the predator might okay, take the prey as its food. Okay, for example. Okay, so this leads to the decline of the population of the prey, right? Decline. Okay, so decline, that's why we have negative sign. While for the second equation, okay, the second equation, I explained this already. The right hand side term, negative by, comes from the second assumption. Okay, when the prey absence, So means the predator may decline, okay, because there is no food, okay. Logical meaning like that, there is no food for the predator, so its population decline at a natural rate. So that's why we have in this equation negative by. The last term here comes from the third assumption. So the rate proportional with the frequency of encounters. So the same term here, but since the rate for the prey and for the predator may be different, so that's why we use different constant here, P and Q. Okay, but the sign for predator will be positive because when prey exists, so it will lead to the growth of its population.